we start talking about electron configurations, I want to review something with you. So I know you guys are now familiar with the idea that there are shells of electrons, energy levels. So we have that primary quantum number n just tells us what energy level we are in. 1, 2, 3, 4, etc. Okay? The energy levels also have sublevels, S, P, D, and F, right? Now, not every energy level has all of those sublevels. Okay? If you were in the first energy level, all you have is an S sublevel, which means the shape of that is going to be roughly a sphere. But if we move into energy level 2, we're now capable of having both an S sublevel and a P sublevel. And I think that's something that people have a hard time visualizing. So I have a visual for you. So imagine inside of here, there is another ball that's down one energy level from this. That's the N1 energy level, where we can only have an S orbital that's a sphere. Then we get further from the nucleus and we get that 2s sublevel, the S sublevel that's in the second energy level. But you can also see there are the 3 P ones as well. Here, there's 1, there's 2 in this direction, and then there's 3 that's up and down. Okay, so see how they're together because they're in the same energy level? So it's not like these are separate things. They're areas where electrons are likely to be located. Then if we go up into the third energy level, now we're capable of having not only an S and a P, but we're also capable of adding in the D orbitals to the mix. Okay, so you can see we've added D orbitals, and then here's with the weird D orbital also added in. Okay? So remember that we have S, P, and D, and then when I add F in, which I don't have an image of F because when you add F in, this becomes essentially very difficult to look at. But you could also add those F orbitals in, but you won't add them in until you get to the fourth energy level. So I just wanted to give you a little bit of a visual of what those sublevels look like. Yes, they are sublevels in the sense that they break the level up into multiple parts, but it's not like we have a ball and then outside of that ball we have the p orbitals. They are kind of in the same areas. And today we are going to cover electron configurations, which is basically us determining what order these orbitals fill in, because we have electrons for every atom. So how do we determine when electrons are in an s orbital and when they're in a d orbital and when they're in a p orbital? How do we figure that out? That's what we're going to talk about today, okay? So if you want to hop over to the notes, we'll get started. The objectives that we're covering today is, first and foremost, you're going to define electron configuration. What even is an electron configuration? Then there are 3 principles that guide how electrons fill in the orbitals around an atom. You're going to be able to name each of those 3 principles for me and tell me how they affect the electrons, what they tell us about the electrons. And then lastly, you are going to be able to write electron configurations. We're going to cover 3 different types of electron configurations today. We're going to cover orbital notation, electron configuration notation, and noble gas notation. Okay? They all 3 have a purpose. There are times when one is more useful than the other, so I'm going to teach you to do all 3. Okay, we'll get started. The quantum model is superior to Bohr's model and to Rutherford's model and to the plum pudding model because it can describe the electron configuration. Simply defined, electron configuration is the arrangement of electrons in an atom. So how are those electrons arranged in space around the atom? And this is for atoms other than hydrogen, because hydrogen only has one, and so it's very easy to tell where that electron is going to be. Okay. Like everything in nature, atoms are seeking to have the lowest possible energy state. They do not want to exist in an excited state. They want to exist at their ground state where their energy is the least, because that is the most stable conformation for them. The lowest energy arrangement of electrons for each element is what we call their ground state. We talked about that a little bit when we talked about Bohr's model of the atom. While real atoms are not built one proton and one electron at a time, this is how we're going to generate electron configurations. In order to make an electron configuration, you first need to know the energy levels of the orbitals. So we have been talking about all of these different orbitals, but we haven't really discussed their energy levels. Okay? And this is kind of what we're looking at. Okay? So I want you to note down here at the bottom, we have our 1s orbital. So that is the s sublevel in the first energy level. Okay? And as we know, the first energy level is only capable of holding one orbital, and it has to be an s orbital, and that orbital can hold 2 electrons. And I want you to notice that when we move up to the next energy level, into the second energy level, we have gained energy, and we've also moved further from the nucleus. Okay? Notice that the s orbital here is slightly lower in energy than the p orbitals. Okay? So while they are in the same energy level, the p orbitals have slightly more energy than the s orbital. And the same thing is true when we go up to the third energy level. We have the s orbital being slightly lower, and then the p orbital being just slightly higher than that, and then the d orbital is even higher. Okay? So what that means for us is generally when we are filling electron shells, we fill from lowest energy to highest energy. So if you have empty orbitals in the second energy level, they will fill before you fill any in the third energy level. These are not going to fill before these are full. I do want you to notice something though. What do we notice about the 4s energy level? Yes. So the fourth energy level, the s orbital, has slightly less energy than the third than the d orbitals in the third energy level, which means this will actually fill before these fill. Okay? In order to fill in the correct order, this is sort of the order they are going to fill in. Okay, so you can notice down here at the, oh, that's not what I wanted to do, sorry. Down here at the bottom, we have the 1s, and then the 2s and the 2p. Okay, that makes sense. There's no 2d because this energy level isn't capable of holding it, so now we move on to the 3s and then the 3p. But remember that the 4s was slightly less energy than the 3d, so it's going to fill first, then the 3d, and then we move on to the 4p, and then the 5s, which is slightly lower energy than 4D, and then 5P, and then 6S. And then you can see that the fourth energy level is capable of holding F orbitals, but they are higher in energy than the 5P and the 6S, so they fill afterwards. Okay, and then if you're looking at this chart, you're following it this way to figure out what order things fill in. I will provide you with a chart like this on the test. So you do not have to remember all of this off the top of your head, okay? Once we understand their energy levels, we can add electrons one at a time following our 3 basic rules. Rule number 1, the Aufbau principle. This means an electron will occupy the lowest energy orbital that can receive it. So just like I was talking about on those previous slides, they are going to fill lower energy orbitals before they fill higher energy ones. So if there is an orbital open with room in it, then they are going to fill that one first. This is why for hydrogen, which only has one electron, that electron occupies the 1s orbital and not the 3p orbital, because the 1s orbital is open and it is the lowest possible energy state for that atom, so it is going to fill that orbital. It could theoretically be in the 3p orbital, but that would put the hydrogen atom in a very excited state, and that is not the state that that hydrogen atom wants to be in. It wants to be in its ground state, so it's going to fill that 1s orbital instead. And then just a reminder to notice that the 4s orbitals are slightly lower energy than the 3d orbitals, which means they fill first. So it doesn't necessarily always go by energy shell, but it goes by which orbitals have lower energy. Yes, generally speaking, as we go up in energy levels, we have more energy, but sometimes there are little exceptions to that rule. The second rule is called the Pauli exclusion principle, which means no two electrons in the same atom can have the same set of 4 quantum numbers. You are already familiar with this rule. It's just the justification behind why 2 electrons can exist in the same orbital, but only 2, and they have to have opposite spins. They can't have the same spin. So each orbital can hold 2 electrons, and their spins must be opposite to each other because of the Pauli exclusion principle. And then our last rule is called Hund's rule. Hund's rule is that orbitals of equal energy are occupied by 1 electron before any orbital is occupied by a second electron. And all electrons that are in singly occupied orbitals must have the same spin state. This means when we're filling orbitals that are all of the same energy level, like p orbitals or d orbitals or f orbitals, each orbital gets filled with 1 electron first, and they all have the same spin, and then we go back and fill them in with a second. You've seen me do something like this when I draw the lines representing orbitals when we were talking about quantum numbers, and I said first we fill them all with 1 electron, and then we come back and fill them with a second. And you'll notice that I started with them all spinning up, because when they are being occupied by just 1 electron, all those electrons need to have the same spin, and then when I go back and fill them in, I fill them with the opposite spin. Okay, now that we have learned what an electron configuration is, and we have learned the 3 rules for writing them, now we're going to look at the different ways you can write an electron configuration. The first one is called orbital notation. In orbital notation, we represent orbitals with lines or boxes, and we write the names under or sometimes above them, and individual electrons are indicated with arrows that either point up or point down to represent spin. So here is an example for you. We have used oxygen. If you look on the periodic table, you will see that oxygen has an atomic number of 8, which means in neutral atoms, it will have 8 electrons. So we are going to write these electrons and show which orbitals they're occupying. Okay. So if I was going to do this from scratch, I would have either a box or a line. I'm going to use lines. Okay, so first thing, I know it's going to fill the very first orbital first, which is the s orbital in the first energy level. So that's why it says 1s underneath. And I know it's going to fill with 1 spinning up, and then it's going to fill with 1 spinning down. Then I know we're going to move on to the second energy level. I can figure out what order by looking back at those charts we looked at earlier in the section. We just look back at the charts to figure out what order these are going to fill in. So next up is the s orbital that is in the second energy level. So we call it 2s. Again, this is going to fill up and then down. Then we get to the p orbitals that are located in the second energy level. And we know that there are 3 of them. So this time, we're not going to fill the first one like this, like we did on the others, because of which rule? Which rule says we fill one at a time? Go back and check for me. Yes, Hund's rule says that when orbitals are the same energy level, we fill them one at a time first, and that those first electrons are going to have the same spin. So now I count up. I have 1, 2, 3, 4, 5, 6, and 7 electrons, but I need a total of 8 electrons. So I am going to go back to this first orbital and give a second electron, this time spinning the opposite direction. And that would give me my final electron configuration written in orbital notation. The only thing I have to do is label these last orbitals as the p orbitals in the second energy level, so the 2p orbitals. Let's pause for a second. Let's do an example. Why don't you go ahead and write me the orbital notation for nitrogen, please? So on the periodic table, how many electrons does nitrogen, how many protons does nitrogen have? Let's start with that. Okay, so its atomic number is 7, which means we're going to have a total of 7 electrons. So this is just information for us to double check ourselves at the end. Okay. The very first energy level that we're going to fill is going to be which energy level? The 1s. Yes, the s energy level in the first, or the s orbital in the first energy level. And because it's the only one at that energy, we're going to fill it. So we have 2 electrons so far. Then what energy level are we going to fill? The 2s. We're going to go up to the second energy level and fill its s orbital too. It's the only one at this energy level, so we're going to fill it completely. Now we have 4 electrons. What are the next orbitals up in terms of energy level? The 2p, we know there are 3 of them. Okay, and then we're going to fill them one at a time because they have the same energy level. So they get filled. That puts us at 7 electrons. So none of these 2p orbitals need to get filled double. And that is the orbital notation for nitrogen. Good work. Okay, now we can move on to the next type. The next type is called electron configuration notation. We do away with lines and arrows. Instead, the level designation, so the 1s that we used to put underneath the line, is given an exponent to represent the number of electrons that exist in that orbital. So instead of drawing 1s and physically drawing 2 electrons in it, we would just write 1s with an exponent of 2 to represent those 2 electrons that are in it. This is what the electron configuration notation for oxygen would look like. So instead of having those individual lines, and then filling them in with electrons with arrows to represent the electrons, we just use exponents. This is great because it saves us some space. It's a little less clunky, but it doesn't give us as much information about spin as the other one. With electron configuration notation, you have to understand how many orbitals you're dealing with and what the spin looks like, because 2p4 doesn't tell you how many orbitals you have or how many of them are individually filled and how many of them are doubly filled. So that's information that you will then have to provide yourself if you're asked a question about it, whereas with orbital notation, you can just see it right away. When we are looking at electron configuration notation, we can double check ourselves by taking the exponents and adding them together, and their total should equal our number of electrons. So in this case, 4 plus 2 plus 2 is 8, which is how many electrons oxygen has. So this is good in terms of number of electrons. Elements of the first and second period, so those first columns on the periodic table, continue to fill rows, continue to fill sublevels following the Aufbau principle. No electrons can occupy a higher energy sublevel until the lower sublevel is filled. When one shell is filled and the one above it begins to fill, that shell becomes inner electrons as they are no longer the outmost energy level. So when I have filled the 1s energy level, not what I wanted. I want to draw. I have my atom, right? This is the 1s, just the first energy level. When it's full, then we go out here, and the 2s and the 2p orbitals begin to fill, right? So that makes this an inner energy level, and this becomes the outermost energy level now. And then if I fill the 2s and the 2p and I move on to the 3s, then the 2s and the 2p also become inner energy levels, and the 3s becomes the outermost energy level because it's the one currently being filled. When an atom, such as neon, has 8 electrons in its outer shell, we say it has filled its octet. These atoms are the last electrons in their period and are called the noble gases. So let's look at a picture of the periodic table. Okay, so if you're looking at this periodic table, okay, hydrogen has 1 electron, helium has 2, so helium filled that 1s sublevel, right? Because that first energy level has 1 orbital, the s orbital, and it can only hold 2 electrons max, so that is full. Helium's outer shell, the 1s shell, is full. But then when we move on to lithium, lithium has 3 electrons. So that 1s is full, but now we've moved up to fill the 2s to start filling it, and that outer shell is not full, right? Beryllium fills the 2s, but there are still 6 spots open in the 2p orbitals. And when those get full, neon, its outer energy level is the second energy level, right? Because it already filled the first one. 1s is full, and now it filled 2s and 2p. So the second energy level, its outermost energy level, has 2s electrons and 6p electrons for a total of 8 electrons. So we would say that neon has filled its octet. its outermost energy level, whichever energy level is on the outside of the atom at that point, that is in the process of being filled, it has 8 electrons in it and is therefore full. This is an incredibly stable formation for most atoms, which is why this column, where that is the case, is some of the most stable and least reactive elements on the periodic table, and we call them the noble gases. My high school chemistry teacher liked to refer to them as the happy campers. They are full and satisfied. They don't really want to lose any electrons, and they don't really want to gain any electrons. They're stable where they are, which means they're not likely to get into a chemical reaction with another atom. Hop back in on our slideshow. Noble gas notation is the final method for writing electron configurations. That's why I had to introduce you to the concept of a noble gas. Okay? This method replaces the first portion of an electron configuration notation with the most recent noble gas in brackets. So you can imagine, okay, for neon, which we just talked about, right? It has the electron configuration notation of 1s2, and then it's 2s2 and 2p6, right? So if I had to write this out for neon, that's not a big deal, right? But as we keep going, you can imagine if we're then going to go 3s2, 3p6, 4s2, 3d10. This is going to get long, right? And so what people want to do to simplify this is to take this section that represented neon, and instead of writing all of that out, we would just take the chemical symbol for neon, put it in brackets, and only write the portion of the electron configuration that was different from neon's on the outside, therefore shortening how much I had to write. Rest of the notation is written out the same as electron configuration notation. It's just shorthand notation. It makes it easier to write out electron configurations for atoms that have many levels and sublevels of electrons. Here's an example noble gas notation. This is the noble gas notation for silicone. Okay, so you can see that like neon, it has the 1s, 2s, and 2p orbitals filled. So instead of writing 1s2, 2s2, 2p6, we just write neon in brackets. And then we can go 3s2 and 3p2 because neon has those initial, 10 electrons. And then silicone has an additional 4 on top of that. So it would fill the 3s orbital, but it would only put 2 electrons into the 3p orbital. Atoms that are in the 4th, 5th, 6th, and 7th periods continue to fill as predicted by the Aufbau principle, with a couple of exceptions. Chromium, we wouldn't predict it to have this configuration where an electron is added to a 3d orbital and another leaves the previously full 4s orbital to make the 3d orbitals singly full. In the case of chromium, as well as several other atoms in periods 5, 6, and 7, there isn't a simple reason for why they deviate from the Aufbau principle. The best explanation is that for whatever reason, these configurations are in some way more stable for the element than the predicted configuration, and so they take them. In addition, the 5d orbitals and 4f orbitals are so close in energy level that sometimes we see deviations there as well. I am not going to expect you to have memorized these deviations, and I promise not to give you problems on the tests or on your homework where you need to know these deviations. I just want you to be aware that as simple as we try to make things in chemistry, sometimes things don't always follow our predicted rules because sometimes nature has a way of making things difficult for us. So there are a few minor deviations that you could expect to see. We don't have simple explanations for them, so the explanation I will give you is just that for whatever reason, they are more stable, and that is why the electrons take that configuration. But for the purposes of your homework and your tests and anything else we do in class, we're going to follow the Aufbau principle pretty close. This is the end of our notes. I am not assigning you the end of section homework today because I would like a chance to do some example problems and practice with this before I assign you any independent homework. So tomorrow in class, we will run a bunch of example problems on the board and you guys will do them on paper. That way you become familiar with how to do these, and then you will get assigned some homework where you have to do them on your own. Sound good? Okay.